All right, welcome to MFC Group's FasTech seminar series hosted by EAS Sales, Mel Foster, TMC, and WestTech. Thank you for joining us this morning. Today, we're spotlighting power management solutions for industrial and commercial applications with Diodes Incorporated. Our speaker for this seminar is David Hyman, Field Applications Engineer for Diodes Incorporated. David spent 18 years in design engineering and engineering management for industrial instrumentation and control before he transitioned to applications engineering for distribution and manufacturers representatives, which he did for 22 years. He then joined Diodes 4.5 years ago as a regional FAE covering the North Central region. Everyone's muted, so please type any questions you may have into the meeting chat, and we'll monitor the questions throughout the presentation and be sure to answer them at the end. And be sure to stick around for following the Q&A for a fun round of trivia. And with that, Dave, I will turn it over to you.
Okay, well, thank you, Amanda, and thank you everybody for taking time to join us today. For Diodes Incorporated, we're going to go through some, more techniques for power management design. So, with that, let's dive into this. Okay, so today I'm going to run through basically some base good design practices when you're doing a power management design. And we're going to look at efficiency considerations, managing thermals, minimizing EMI, some sequencing techniques, ways to keep your design compact and modular. And then, of course, at the end, time permitting, I'll go through a little bit of Diodes corporate propaganda. Otherwise, my bosses will get mad at me. So, all right. So, when you are in the midst of your design, your system design, basically you're starting out and you're in your architectural phase. You're picking processors, other components that you need in your system. But while you're doing this, the whole time, you should be always considering what your power tree is going to look like, right? And as you're doing this, obviously you're going to have different priorities, right? So, some designs are more key on efficiency, especially designs that are battery operated and so on. Thermals, another big consideration, typically EMI compliance, again, depending upon what the end product is or your end market, that can be a big consideration as well. Modularity and board space, basically when I say modularity, once you establish a working power design or a power segment of a power design, like an individual rail or something like that, if you basically modularize it in your design tools and stuff so you can basically reuse it, that's just a handy way of becoming more efficient in your overall power supply design tasks. And then we'll look at the power tree sequencing, bringing your power supplies up in the right order. And in some cases, second sources for your AVL could be another big consideration too. A lot of you will have requirements or mandates from your sourcing groups that you have to have at least 2 or more approved sources for every socket if possible. So let's dive in. Okay, so let's start with efficiency. So what affects the efficiency of a DC to DC converter? Switching speed obviously has a pretty significant effect on how efficient a converter is going to be. Other things are things like conduction losses, and buck and boost converters. Another thing that affects their efficiency is how close the V in or the V out voltage is to the V in voltage, right? The further they're apart, the less efficient a converter will get. And again, that'll have bearing on how you design your power tree. And then modulation schemes, again, will have effects on efficiency depending upon whether you're using a PWM, a PFM, constant on time, or one of these other modulation schemes to control your converter. Those can have effect on how efficient it is as well. So we're going to start here by looking at a basic power tree spec, let's call it. So this is actually a spec we received from one of our customers, right? And they sent this to us. You can see here in the circle here, this basically gives us their required outputs. This particular power tree requires 4 different outputs, and they're giving us here what the maximum power requirement for each of these rails is. They're also giving us the output noise requirements for each rail, the sequence that they need, and then in addition to the maximum power, they're giving us what the average power is for each rail too, and what the actual power calculation there in the green part of the text. Okay, so again, this is a pretty basic power tree. It's a VN 12 volts, max power approximately 10 watts, average power about 5.2 watts. But this is actually for an automotive application, hence the 12-volt VN nominal. But this could be for any industrial, commercial, medical type application as well. So this is just in general how we would look at a power tree. So when we take a look at this power tree, the first thing that we notice for output power is the bulk of the output power is being consumed by the lower voltage rails, the 0.8 volt and the 1.8 volt. So basically the V core and processor power is using the bulk of the energy coming out of this particular power supply, right? So that's going to have an effect on how we take a look at this if we're designing for efficiency. Because again, remember that I said efficiency of a DC converter is affected by the difference between the input voltage and the output voltage. So you take a look at these graphs here that I'm showing, and we're starting here at the most efficient here atop this blue trace. This is with a VN of 12 volts and a V out of 5 volts, right? So again, this is giving you efficiency starting in around 80% and going up into the mid 90s, as the output current increases. And again, we'll take a look at how the efficiency of the converter is affected by at what particular load we're delivering power. Okay. So as we get as the difference between the input and output voltage increases, because you see here at the bottom of this purple trace, the VN is 24 volts, the output is 3.3 volts. This is our least efficient scenario here. So we're actually down into the 60% range, and we never get above the mid 80s here at that much delta between the input and the output. Okay, so it does have an effect, that input to output voltage difference does have a significant effect on the efficiency of the converter. So we take a look at the power tree that we came up with for this particular customer. You'll notice here that we have the 12 volt in. Since this is an automotive power tree, we're including the reverse polarity protection, which is an ideal diode controller in this case. We also do the first stage buck. So when I was designing power supplies, the conventional way was always to take a look at the highest voltage rail that we had in the system, which in this case is this 5-volt rail here. And we would do this first buck down step from 12 volts. We would typically buck this down to between 6.5 and 7 volts typically, so we have enough headroom for the converter. And if we were to do that, that would create a much higher difference in input voltage between input and output voltage for these two, where the most power is being consumed in this particular design, right? So we have, in this case, decided to take this first step from 12 volts down to 3.7 volts. So we're doing our bulk buck down here, even though we have this 5-volt rail. We did this basically because when we look at the average power of this rail, it's 0 basically. So this is a rail that is not on all the time. So rather than decreasing the overall efficiency of the power tree by doing this first step at something above this rail, we decided to go down to a rail that was going to basically be most efficient or more efficient, providing where the most energy of this power tree is going to be consumed, which is at the 0.8 volt and 1.8 volt rails. Okay, so basically I'm just showing you this to kind of give you the feel for when you're designing for efficiency. You can think a little bit outside the box. Boost converters are generally not as efficient as buck converters. So we generally don't like to use them, but in this case, since this rail, the max load is so light and the average load is 0, we decided that we were going to basically do this particular rail as a boost rather than a buck, which is slightly less efficient, but it keeps the overall efficiency of this entire power tree higher because we're basically decreasing the voltage difference between the 0.8 and the 1.8 volt rails and the input voltage, okay? All right. So that's one aspect we're going to take a look at. So another aspect I was talking about is the modulation scheme of the converter. Typically, diodes, DC to DC converters, basically, most of our AP6000 family offer the option of either PWM or PFM modulation. You can get parts or SKUs that have PWM all the time. We provide converters that are PFM all the time. We also provide converters that automatically switch between the two modes, and I'll explain to you why we do that in a minute. But so we can see here with PFM modulation, that's this top graph right here. This is PFM. The converter remains fairly efficient even at very light loads. So we're basically showing this down around 2 milliamps. We're still around 80% efficient. And then as we increase our output current, we're going up, and we're showing the 5 volt and 3.3 volt versus a 12 volt input here. We're getting up into the mid 90s here at a 5 volt out, and we're staying in the, at least the low 90s at 3.3 volts out with PFM modulation. PWM, and the reason why we like to use PFM and light load is basically PWM modulation makes the converter very inefficient at light loads, right? So at light loads, if you can tolerate the ripple, it's better to run the converter in the PFM mode to remain more efficient overall. And then we switch to PWM at higher output loads, obviously, because efficiency is pretty much equivalent at PWM at higher loads. However, the output ripple of the converter is much lower in PWM mode than it is in PFM mode, okay? So that's why we offer converters with either PWM all the time. If you're always going to be in the moderate to higher loads on your converter, PWM is fine to have that all the time. It keeps your ripple minimum. Some customers prefer to have PFM all the time because they always want as much efficiency as possible and they can tolerate the ripple. And others prefer the converters that'll switch back and forth so that they have the lower ripple at higher output loads, but the light output, they can tolerate the greater ripple and have the higher efficiency. All right, so let's talk a little bit about switching frequency and how that affects the efficiency of the converter. So I'm showing here, this is one of our design calculators. This is the front page of a design calculator. This basically just allows you to see what's happening with the converter, sorry, from a power loss and efficiency standpoint, while you basically can play with the, your input and output voltage specs, your inductor, and some of the other components in your system. So this one I basically set up for a switching frequency of 500 kilohertz, an input voltage of 12 volts, the output voltage of 3.7, which was, this is our first buck down in that original power tree that I was showing you before. So at 500 kilohertz, you can see here that our efficiency is basically, pretty good. I mean, this again is PWM mode I'm looking at. So we are basically very quickly, when we get up into a few hundred milliamps, we get up above 90%, and we stay above 90% this whole way at 500 kilohertz, right? And you can see here when we look at power loss distribution, the blue parts of these bars are actually the conduction losses, and the red parts are the switching losses. So you can see that the losses in this particular scenario at 500 kilohertz with the components we have selected, the power losses are dominated by the conduction losses. I'm sorry, the conduction losses versus the switching losses, okay? So now if we take the same conditions of the 12 volts in, 3.7 volts out. And I did make an adjustment to the inductor because our tool basically recommends an inductor. I try to keep that inductor as close to what the recommended value is, again, because that helps the efficiency of the converter overall. But even changing the inductor, when we go up to 2 megahertz switching, you can see here that our efficiency has dropped down into the mid 80s, right? Mid to low 80s. So we lost almost 10% of the efficiency of this converter just by going from 500 kilohertz to 2 megahertz. And we know that the appeal to doing this is obviously it keeps your passive components smaller. So we have a physically smaller inductor now, which obviously from a standpoint of your bill of material costs and so on, the smaller the passive components, the less expensive they're going to be typically. So there's a lot of reasons why you would want to have converters running at higher switching frequencies, but just keep in mind when you do it, you're paying a penalty in efficiency. So if your goal is to maximize efficiency, the choice would be better to basically stick with a lower switching frequency overall. All right. So moving on, I'm going to touch a little bit on thermals. Okay. So when you're doing your design, obviously, particularly your power tree design, obviously thermals are going to be a consideration. How much board real estate do you have available? How much copper area do you have to pull heat out of the parts and so on? So when you look at our data sheets, typically we give you 2 different R theta values, right? So the thermal resistance of the package, right? So we give you the R theta junction to case, and then we give you R theta junction to ambient. And we would give you R theta junction to ambient. We do it usually based upon what we call the minimum pad layout or the suggested pad layout, right? So if you put your converter down onto the PC board with this minimum recommended copper layout, this R theta junction to ambient that we're giving you here, 45 degrees C per watt, is based upon this much copper. Now you can lower this 45 degrees C per watt by increasing your copper area. On some of our data sheets, we provide R theta junction to ambient in 2 ways. We provide it with the minimum pad layout, and we'll also provide it with somewhere in the area about 1 square inch of 2-ounce copper. So we'll be able to give you basically the relative difference. So when I talk about these junction to ambient and junction to case thermal resistance, basically, the only one of these the Diodes has any control over whatsoever is R theta junction to case. That's the only thing that Diodes directly controls. When we give you junction to ambient based upon this, we have no control over what the junction to ambient is. We're just giving you this value as a reference based upon the measurements we took with this pad layout on PC board, right? So junction to ambient is always 100% dependent upon how the customer handles the thermals on their PC board. So again, we like to give you this as a reference so you can see our resistance junction to case is 5 degrees C per watt. The junction to ambient with this pad layout is 45 degrees C per watt. This, again, we can lower this 45 degrees C per watt by increasing the amount of copper that you have underneath the part to pull heat away from it. Okay? We actually have a couple of application notes that basically speaks to this. It's our AN 1157 and AN 1100. We'll give you some more insights to understanding how do you interpret our data sheets and how to basically handle your copper area allocation for your basically thermal performance. All right, so another thing that we do for you is on every data sheet for a DC to DC converters, we give you this recommended pad layout, okay? And a lot of cases when we give you a R theta JA based upon the larger copper area, this would be basically the layout that we would be basing that on, all right, in most cases, right? I'm not sure if this is exactly 1 square inch of copper here, but it would be something close to that, right? So we give you this layout basically for a couple of different reasons. I'll touch on the EMI aspects of this in the upcoming slides, but from a thermal standpoint, we show you this ground plane here. We show you the vias and how we recommend that you place them into the ground plane on the PC board. We're assuming you're going to have a ground plane in a middle layer of the board, and this would basically be a good way to or a good, how shall I say, distribution of vias in order to get heat from that surface layer down into the ground plane layer and spread it out and pull it away from the part, okay? Right. Let's move on. So touching on EMC now. So general guidelines for, EMI, EMC, and again, we have an app note that touches on this as well. But this, again, just in general, when you are placing your components on your PC board, it is good general practice, especially if you have components like this that are switching and you're basically going to be generating both conducted and rated EMI, is to bring those parts away from the edge of the board and put a guard ring, a ground plane guard ring around them. Okay, so we're kind of showing you here an illustration of when you're placing that signal trace towards the edge of the board, and it's got some sort of a switching or AC signal in it. It is basically has with no ground plane at the edge of the board to absorb any of this energy. It's all going to radiate out off of the board, right? So we say pull these traces away from the edge of the board, put this guard ring around them, basically, and have the ground plane in the board, as much ground plane as possible underneath the parts, basically to help absorb some of this RF radiated energy. All right, that's going to help you in your EMI compliance. And then for layout considerations with regards to EMI, some of the areas that are the biggest contributors to your EMI, basically, number one is going to be the switching loop. So the switching loop on a DC to DC converter is typically, you come out of the switch node into the inductor and down to your output cap. So this loop here between switch node to ground is your switch loop, right? And on our layout or our reference layout here, we're showing it right here. So this is the switch node or the switch pin right here. Here's your inductor and here's your output cap, right? So we are keeping this area inside this loop here as small as possible because we know the gain of an antenna is directly proportional to its internal area, right? So the smaller and tighter we can keep this loop, the better your EMI performance is going to be, okay? So switching loop, again, very important for rated EMI. As far as conducted EMI, most of the conducted EMI coming out of the part is going to be coming out from typically the V-in pin, right? So we talk about the V-in decoupling loop here, right? So the V-in decoupling loop is right here on the schematic, right? It's V-in, and then you have your input capacitor. So we typically like to see the V-in capacitor placed as close to the part as possible. And we want that V-in loop to be as tight as possible too. So we're bringing that V-in loop or the V-in out. We put the bypass or capacitor or the input capacitor right here, very close to it and directly into the ground plane, okay? So doing that is going to help with your conducted EMI back out of this part. The other thing that I'll make note is, typically on your input caps, you're using fairly high value capacitors, which means generally the case sizes are going to be larger. when you're looking at ceramic caps for bypass, these multi-layer ceramic capacitors, the smaller the physical case size of the capacitor, the better performance it's going to have for high frequency decoupling. So we don't show it in our reference design here, our reference that we don't show it here on our schematic, but it's good practice to put a small case size capacitor at your input, potentially a lower value, close to this V-in capacitor as well to help basically decouple or shunt the high frequency noise directly to ground, because you're going to have better performance with a smaller case size. So this part here could be a 04, 02, 06, 03, 08, 05, whatever size it would need to be. But going into the 0201s, 0402 is okay, but 0201s and even smaller size capacitors will give you better high frequency performance at your V-in decoupling. All right. And then the feedback network here, where we show on the schematic right here, the feedback network is basically just the resistive divider you're using to set your output voltage, right? Going into the feedback pin here. So we want you to keep that, again, as close as you can to the part. We want the output trace coming to this as tight as possible, or as close as possible, or short as possible, and keep this very close to the part, keep these parts close together, and keep this as tight as possible. It will give you better regulation performance if you have as minimal noise on these as you possibly can. All right. And again, we have an application out, our AN 1191 talks about all of these EMI points that I basically we're just giving you an overview of right here. Definitely just good practices for keeping your EMI design as tight and minimum EMI as possible. So modularity is another thing I was talking about. Doesn't necessarily directly affect the efficiency, but when you were doing your power tree designs, what I show here basically is just a bunch of these reference layouts from our data sheets. But if you basically create these as modules or puppets in your EDA tools, and basically just bring them in and place them into your designs, it's going to basically decrease the amount of time you spend, and it's going to kind of help you basically keep these layouts efficient as possible from a thermal and EMI standpoint in successive designs, right? So just again, just a good practice. And if you talk to us nicely, I might be able to talk some of our business unit people out of getting these for you in Gerber format as well. So at any rate, so let's talk a second a little bit about sequencing. For the power tree that we showed initially, remember they had a specific sequence that they wanted to follow. And the way that we decided to do that is, and a simple way to do it in practice is your DC to DC converters, a lot of our parts actually have a power good pin, and then you typically have an enable pin. So if you want a supplies to sequence, in this case, we wanted 3.3 up first. We want 1.8 to come up roughly at the same time, and then we want these other different rails basically to just come on in succession. If you take the power good pin and basically just connect it to the enable pin of the next supply you want to come up, basically you could just get these supplies to cascade and power up. These power good pins on DC to DC converters typically on board, what it is actually just a window comparator. So when you're within a percentage of whatever our window is of the correct output voltage, with a slight time delay and some hysteresis, we will basically assert this power good pin. And then as this is asserted, basically it can turn on the next supply, the next supply, and the next supply. Other ways this can be done is we can do a coincidental type sequencing. You can see here how this is going to perform actually. So you're going to get both parts that start ramping at the same time, but they will come up basically in order of their output voltage. Typically, you're taking the 5-volt output and you're bringing that into the soft start or tracking input of the next converter. So that's another methodology, again, coincidentally. And then you have ratiometric. So basically, if you just take and connect tracking inputs together on converters, basically they will come up ratiometrically as power comes up. I mean, it's still going to come up the lowest output first, typically, but I'm sorry, they'll come up basically roughly at the same time, but they'll come up ratiometrically. All right, so that's kind of the techniques I wanted to touch on today. Then if we take a look at some application examples, this is one I wanted to touch on. Many of you use PMIX in your designs, and obviously that's a lot of these larger MCUs, SoCs, and so on, actually come with or have PMIX available that are really nice because they bolt right up to the part, provide all the necessary power rails and sequencing and everything. They also add additional functionality by giving you the ability to throttle the V core voltage depending upon what the performance requirements are of whatever application that's running on the processor at that given time. So they are really slick parts. The downside to these, in some cases, is the fact that, number one, they're expensive. Number two, they're proprietary. So now you have two parts on your design because the SoC or the MCU, typically, you're never going to be able to second source. But when you actually add the PMIC in there, there's another part that's a proprietary part that just basically increases the risk of having supply chain issues if we get into a constrained market again. So what we have done at the request of several customers is we've taken a look at these PMICs, and what we basically do is we'll come up with a equivalent power tree for you using discrete DC to DC converters, LDOs, or load switches, and basically emulate these output voltage and so on, and control the sequencing and so on. I mean, you do lose some of the functionality of the PMIC. In other words, we don't give the ability to automatically control to throttle the V core voltages and so on. And obviously the software libraries from the processor don't have the drivers and so on to run, they won't run our discrete design, obviously, the way they'll run the PMIC. But again, in some applications, in some cases, we had customer basically that had a line-powered device that had a small operator interface on it that was powered all the time. They really weren't concerned about, low power modes or anything like that. So they were strictly concerned about cost and second source ability. So they approached us and had us come up with basically an equivalent design for this. And basically, this is what we did for them. We came up with this power tree to replace that PMIC. We handled the sequencing the way that I was talking about, using power grid to enable basically to have all these supplies cascade as they're coming up. And when we did this design or this proposal for the customer, we found out a couple things. Compared to the PMIC, our bill of material cost for our discrete DC to DC converters and external components came up to be less than the cost for the PMIC with its external components. So, and it was like 10 to 15% less. The other thing we found out is using this modularity idea, and we put together basically a proposed layout with again using those our reference layouts, created a routable power tree PC board footprint, and found out that we actually took less board real estate than the PMIC with external components took. And again, it was in that 5 to 10% range. So again, there's an opportunity here, right? So in addition to being cheaper and smaller, we did also offer the ability to second source most of these DC to DC converters, because the bulk of our DC to DC converters in this family will drop into typically a TI socket, but there's some TI, there's some or MPS, so there's some Rich Tech. There's a number of different suppliers where we will have a pin-to-pin drop-in, and in some cases a pin-to-pin and bomb-to-bomb drop-in for the other converter. Okay. And this here, I'm just showing you. I guess this was the area calculation we did, where this in this case was an MPS part was 25 square millimeters, and we found ours with our external components would fit into roughly 13.4 square millimeters. So in this case, it was a significant savings. I think this must have been centimeters, maybe not millimeters. Doesn't sound right, but at any rate, it was a significantly smaller board footprint than what the PMIC offered. Here's another power tree that we did for a customer. This was, again, very simple. They had this was, I believe, a water softener control. They had 4 buck converters in their power tree that were all TI parts. Basically, they were all the same TI part. We basically provided them a pin-for-pin drop-in to the TI part. In so doing, we allowed them to have a second source, and we actually, I believe, saved them some money as well. So we got them to convert over to our parts. Right. So I have a bunch of example power trees here that I'm not going to spend a lot of time on. I think we're kind of getting to the end of my time slot anyway, so I wanted to just breathe through to the end and show you, number one, the Diodes product portfolio. Normally, if I was in the room with you, I asked for a show of hands for those people that knew that actually Diodes made things other than diodes. And typically, we still run into people that pigeonhole us as to a commodity discrete supplier. But this, again, is a high-level look of our different product lines that we have. So obviously, we still do have the discrete portfolio, which includes diodes and rectifiers. But we also have a very broad portfolio of MOSFETs. We actually are typically from 150 volts down in silicon MOSFETs, and we are, I would say, from a performance and price and let's say capability standpoint, right at the state of the art on our MOSFETs. So we have some very high performing MOSFETs. Our MOSFETs are very cost competitive. We also have a portfolio of TVS and protection devices, again, for power line and data line applications. We still do bipolar transistors of all different types, and relay drivers, gate drivers, and that sort of thing. But then on the analog side of our portfolio, we actually do have a lot of power management products, the DC to DC converters and controllers. We do the load switches. We do USB-C charging control and USB power switches and so on. A lot of LED drivers. And then we also do some offline products as well, AC to DC converters, synchronous rectifiers, and so on. And then we get into high-speed serial connectivity. So all of your PCIe, HDMI, DVI, any other high-speed serial interfaces. We do signal integrity. We do clock tree type products. We do crystals and oscillators. Again, we own the supply chain for crystals and oscillators, so everything from the quartz bar through packaging and test. So again, Diodes has a very broad portfolio of products, and we actually picture ourselves as not necessarily, we don't provide the SOCs or MCUs, but everything around them in your system. You can basically look to Diodes for a good portion of that. So this is a high-level look at our DC to DC buck converter offering. The slide is a little dated. We do have parts shipping in production at 100 volt and 80 volt now, in addition to the 60 volt and 40 volt down to 5 volt parts. So you can see this is the input voltage range we support. These are the output current ranges we support. Again, at a high level, this particular chart it represents hundreds of SKUs of DC to DC converters. It's kind of illustrated here when you look at the different input ranges. So we start at 5.5 volts, and we go here. This is everything above 60 volts. So this includes 80 volt and 100 volt parts. Converters, we actually have some controllers as well. Again, most of these parts have a pin for pin drop in to another manufacturer. Again, most of it's going to be TI, but we support others as well. So you have the ability now to have a dual sourced power tree in many cases using Diodes parts. Again, I have a lot of backup for that. And I'm not going to go into every one of these. Let me just get here to the end and close out. So the corporate propaganda about diodes that I wanted to talk about, again, this is how we view ourselves. So this is the core of your system, your FPGA, ASIC, SoC, MCU, whatever, all the stuff that goes around it. So power tree, clock tree, signal integrity, power driving, motor driving, power switching, so on and so forth, is where Diodes lives. Again, we have a broad portfolio. We've been in business since 1959, so we've been in business for 66 years now. We have, how shall I say, thousands of employees across the globe. We have semiconductor fabs basically on multiple continents. We have them in the US, the UK, we have them in Asia. We have assembly test in Asia, and we've moved into Malaysia. So we are fully supporting the China +1 bill of material requirements for automotive, resilient supply chains, and so on. Again, we have, again, a very broad product portfolio, and we're here to help. Bring us your requirements for your power trees, your clock trees, and let Diodes show you what we can do to give you great solutions at very competitive pricing.